Decoding a PNG image with JavaScript step-by-step. Decode a PNG means to convert an image from binary data to image data with pixels. Image binary data can be retrieved from canvas, image, object URLs, image URLs, blob. See comprehensive image processing on browser for details. Image data is an object with pixel data, width and height. Example image. This is the example image. It's too small. Let me enlarge it for you. So it's 4 pixels, red, green, blue, and then it looks like a gray pixel that might have 50% opacity. Raw binary data. Let's read raw binary data from input. So we have a input control on HTML page. It's of type file, and then we have a script. Const input equals document.querySelector input, so we're going to get that input element. Input.add event listener change, and then we're going to add an async function, so a callback function basically. Const file equals e.target.files, so that is, I believe, object deconstruction there. I thought object deconstruction used curly braces, but maybe this is object deconstruction for an array, most likely. Const array buffer equals await, file.array buffer, and then invoked. Console.log array buffer, and then the actual array buffer. To do, let's decode the array buffer. Const image data equals decode array buffer, console.log image data and image data. And then we close the callback function and then close the add event listener call. And that is the end of the script. The output array buffer is the following. So it looks like we have a table, and let's see, 0 to 3 are the indices, 4 to 7, 8 to 11, 12 to 15, 0 to 15. Okay, so the top column is kind of like local indices within the row, because this is a stream of data. So we got 0 to 15, 137, 80, 78, 71, 13, 10, 26, 10, 0, 0, 0, 13, and I believe that is the PNG header right there. And then we got some more bits, but I don't really think it's important to analyze this. I think you could pause here if you want to make some sense of this. Each table cell contains 4 bytes. 1 byte contains 8 bits. 1 bit is a binary value 0 or 1. Alright, so just some fundamentals there. PNG signature. A PNG image should start with 8 bytes. 0x89, 0x50, 0x4e, 0x47, 0x0d, 0x0a, 0x1a, and 0x0a. So those are those 8 bytes of the signature, and if we scroll up, we can actually see that signature, but the signature is in decimal here. So these first 8 bytes right here, so right here, that is the signature that is down here. Right here, but this is hexadecimal. That's why it doesn't match the signature you saw in the table above. So let's keep on reading this. 0x means a 16-bit value, so it's just explaining the hexadecimal notation there. 0x89, 0x50, 0x4e, 0x47, 0x0d, 0x0a, 0x1a, 0x0a, to 10-bit values is 137, 80, 78, 71, 13, 10, 26, and 10. And it's just doing a recap of what I just explained earlier. So we have the bits 0 to 3 and 4 through 7 are 137, 80, 78, 71, 13, 10, 26, and 10. And the corresponding hex is listed below. This image satisfies the requirement. So the image has a valid PNG header. And since it has a valid PNG header, we can go ahead and try to get out the chunks. So the chunks are explained here. Chunks. Chunks contain image data. A chunk contains chunk begin, chunk data, and chunk end. A chunk begins with 2 32-bit value. The first is chunk length, and the other is chunk type. Let's begin with a chunk. Chunk begin 1. So we have bits indexed 8 to 11 and 12 to 15, and that is an inclusive index. And the bits are 0, 0, 0, 13, and 73, 72, 68, and 82. And it would really make more sense for this to be hexadecimal, but I didn't write the article. So the length is 13, right? Because you're going to take all those bits, and when you smash them together, you get the number 13. Or sorry, did I say bits? I meant bytes. You take all the bytes, 4 bytes, smash them together, you get a 13. You take the next 4 bytes, smash them together, and you get the ASCII string IHDR. This chunk is IHDR with 13 bytes. Chunk data 1, IHDR. IHDR values are listed below. So we have bytes 16 through 19, 20 through 23, 24 through 27, and 28, and that's all inclusive. And the first 4 bytes is the width, the second 4 bytes creates the height, and looks like depth is just 1 byte, and then color type is just 1 byte, and compression, filter, and interlace, those are all described by just a single byte. Yep, that's what it looks like. Okay, so width and height means image width and height. Depth represents how many bits contains in a pixel, an image composed of pixels, and a pixel composed of channels, and a channel composed of bits. So that's just explaining the structure of how these different data types are kind of like nested together when you're conceptualizing them. Color type. There are 5 color types. 0 is grayscale, 2 is RGBA triple, 3 is palette, 4 is grayscale and alpha, and 6 is RGB triple and alpha. The palette color type supports 1 channel per pixel. By the way, when you want something in a format that OpenGL is going to accept, you want color type number 6, because that's going to be RGBA usually. Or it's ARGB, I'm not sure. I know that RGBA is what OpenGL needs, and I'm not sure on which side the alpha channel is with the PNG compression. Let's just keep going. Compression represents the compression method. Only 0 is supported currently. Represents deflate/inflate. Deflate/inflate is a lossless compression method that uses a combination of LZ77 and Huffman coding. It is used widely in 7-zip, zlib, and gzip. So if you want to know more about the nitty-gritty details, looking at the source code for 7-zip, zlib, or gzip would be a good place to start. Filter represents the filter method used before compression. Only 0 is supported currently. Filter method 0 has 5 filter functions. We will talk about it later. Interlace represents if the image is loaded interlaced. 0 means without interlaced, 1 means with interlaced. Interlacing an image is just a way to pack the information so that when you're on a really bad internet connection that's very slow, the image kind of loads progressively, so you can kind of see like a blurry version of the image before you see the full image, right? So you can kind of get an idea of what the entire image is going to be before the entire image loads. That's the purpose behind interlacing. It's not really something I think is necessary in this day and age, but at the time that the PNG spec came out, we did not have high-speed internet. This image is 2 by 2 pixels, has palette color type, 1 channel per pixel, and 2 bit per channel. The compression method is deflate/inflate. The filter method is 0, and the image is without interlaced. Chunk 1 end. Bits 29 to 32 inclusive are 15, 216, 229, and 183, and those are decimal numbers. Chunk n contains 4 bytes of CRC32 checksum. The decoder should calculate the checksum of the chunk type and the chunk data for each chunk. The calculated checksum should equal the chunk end. Chunk begin 2. Bytes 33 through 36 inclusive and 37 through 40 inclusive. We have 0001, and 115, 82, 71, and 66. The first 4 bytes concatenated together creates a length of 1. The next 4 bytes concatenated together creates the ASCII string sRGB, which is standard RGB. This chunk is sRGB and has 1 byte chunk data. Notice that sRGB starts with lowercase s. This means that the chunk is ancillary. Otherwise, the chunk is critical, like the previous one, IHDR. So an ancillary chunk is a chunk that you can safely ignore if you have no clue what to do with it. Chunk data 2, sRGB. So we have a byte indexed 41 and its value is 1. The sRGB chunk value represents the color space of the image. 0 for perceptual, like photographs, 1 for relative colorimetric, like icons, 2 for saturation, like graphics and charts, 3 for absolute color metric, to show the absolute color of an image. Chunk end 2. Bytes 42 through 45. The values are 217, 201, 44, and 127. That is the checksum CRC32. Chunk begin 3. Bytes 44 to 49 inclusive, and 50 to 53 inclusive. The first 4 bytes slammed together gives you a 9, and the next 4 bytes slammed together gives you the ASCII string lowercase p, hy, which is capital, and then a lowercase s. 9 bytes phy s ancillary chunk. Chunk data 3 phys. Bytes 54 to 57 inclusive, 58 to 61 inclusive, and 62. So the first 4 bytes is the x-axis pixels per unit. The next 4 bytes is y-axis pixels per unit. And the last byte is a unit specifier. So we have 2,835 is the number you get when you slam together those 4 bytes. And it's the same 4 byte values in the next 4 bytes. So it's 2,835 by 2,835, and the units is meters. So the PHYS basically stands for physics, I think, and it's to give the image like an actual scale by telling us like how big is 1 pixel in some type of physical units. That's what the chunk is for. So let's keep on reading. PHYS chunk represents the physical size of the image. As we can see from the table above, the image is 2,835 pixels per meter in width and 2,835 pixels per meter in height. Chunk end 3. The bytes 63 through 66 inclusive, 0, 154, 156, and 24 is a CRC32 checksum. Chunk begin 4. Bytes 67 to 70, 71 to 74, that's inclusive. The first 4 bytes creates the length of 12. The next 4 bytes creates the ASCII string PLTE. 12 bytes PLTE critical chunk. And we know this is a critical chunk because the first letter is capitalized. Chunk data 4, PLTE. We have bytes 75 to 78, 79 to 82, and 83 to 86 for a total of 12 bytes. Remember that these ranges are inclusive ranges of the indexes of the bytes within our byte array. The first 4 bytes, I don't know. It doesn't have a description. It just says the palette is RGB triple, so the data is decoded as the following. Okay, so palette 255, 0, 0, and then another chunk 0, 255, 0, another, okay, so I see what's going on here. It's a RGB triplet, but there's no alpha channel, so you're just splitting this stream of bytes into groupings of 3, and each chunk of 3 bytes is a subarray where each byte goes into one of the 3 slots of that subarray. And for a RGB color, you can only have the range 0 to 255, so all you need is 1 byte to express that. So anyways, when we take that byte stream above and we pack it into a whole bunch of subarrays, we get our palette, and the subarrays are 255, 0, 0, 0, 255, 0, 0, 0, 255, and finally 255, 255, 255. So that last one is definitely white, the first one would be red, the second one is green, and the third one is blue. Okay, so that makes sense. Let's keep on scrolling. Chunk end 4. We got bytes 87 to 90. The value is 251, 0, 96 to 46. Is a CRC32 checksum. Chunk begin 5. We have the bytes 91 to 94, 95 to 98. The first 4 bytes creates a length of 3. The next 4 bytes smashed together creates the ASCII string TRNS, lowercase t, so it is an ancillary chunk. It says 4 bytes TRNS ancillary chunk. Chunk data 5 TRNS. Bytes 99 to 102, with the values 255, 255, 255, and 127. The chunk supplies the alpha value for the palette, so the palette transforms to... Okay, so I see the transparency information is separate, and so we have to edit those subarrays and inject the alpha value into each one of those subarrays. And so now we've edited the palette from earlier and tacked on those subarray values. So we've tacked this on, which comes from here, and then we've tacked this on, which comes from here, and we've tacked this on, which comes from here, and we've tacked this on, which comes from here. It would be kind of useful if they used, different values than this, because it would be easier to see the connection of this value to here, right? But anyways, I digress. Let's keep going. So chunk end 5, we have the byte indices 103 to 106 inclusive, with the values 128, 144, 196, and 89. And that's a CRC32 checksum. Oh, lost my place there. CRC32 checksum. Okay, so chunk begins 6. We got the bytes 107 to 110 and 111 to 114. The first 4 bytes creates a length of 12. And the last 4 bytes creates an ASCII string IDAT. And 12 bytes IDAT critical chunk. And that kind of makes sense. So let's see. 3 times 4 would be our 4 pixels, right? And it's RGB triplets. Actually, maybe not. Let's keep on reading. All right, so chunk data 6 IDAT. We got the byte indices 115 to 118, 119 to 122, 123 to 126. Those are our groupings, right? It's clustered in clusters of 4 bytes. The total range is 115 to 126 inclusive. The first 4 bytes, 120, 156, 99, 16. The next cluster is 96, 216, 00. Last cluster is 0, 228, 0, 193. The compression method is applied to the IDAT chunk when encoding. So we decode it with the zlib.inflate. We can use the library Paco to decode. So I was wrong about my assumption earlier because I forgot the data is compressed. So we need to decompress the data within the IDAT chunk. And I don't think this article is mentioning that before you decompress, you need to collect all of the IDAT chunks and you need to concatenate them together. That is my understanding from what I read in a previous article. So let's keep on scrolling here. So they're going to use Paco to decode, so it isn't go too low level into the deflate method. The decoded data is an uint8 array, 0, 16, 0, 176. We will need more information to decode it. We will learn about the scan line, a little bit about the filter, and the logic to bits per pixel. Scanline introduction. A scanline is a row of pixels in an image. If the image height is 2, the IDAC chunk contains 2 scanlines. A scanline composed of 1 byte filter function type and pixel data. The pixel data is appended directly to the previous pixel data without any extra space. The scanline should be filled to match 1 byte if the rightmost bit is empty. Alright, so we have filter function and then pixels ... fill ... So the filter function is 8 bits, and then we have bits per pixel multiplied by the pixels, and then we add useless bits. So I'm assuming there are, since we have to pack the data into a binary format, and we have to pack the bits into bytes, there is the potential that we have useless bits. I think that's why it states plus useless bits. We need to know the bits per pixel to get the length of each scan line. Okay, so we have color type, channel, depth, and bits per pixel chart. So the color type 0 is grayscale, and the channel per pixel is 1. The depth values can be 1, 2, 4, 8, or 16. The bits per pixel can be 1, 2, 4, 8, or 16. Color type 2, the name is true color. Channel per pixel is 3. The depth is 8 or 16. The bits per pixel is 24 or 48. Color type 3 is palette. Channels per pixel is 1. The depth is 1, 2, 4, or 8. The bits per pixel is 1, 2, 4, or 8. Color type 4, grayscale and alpha. Channels per pixel is 2. The depth is 8 or 16. I believe those are bits because it's color depth. The bits per pixel is 16 or 32. Finally, the color type of 6 is named true color and alpha, so that'd be our RGBA. The channels per pixel is 4. There's 4 channels, the red, green, and blue channel, and then the alpha channel. That's why there are 4. Depth is 8 or 16, and the bits per pixel is 32 or 64. The color type 3 represents that 1 channel data per pixel. The image depth is 2. So we now know that the data contains 2 bits per pixel. So the scanline decoded is scanline bits. We have 3 columns, rows, filter function, and then pixels, ... open bracket, fill, ... close bracket. Okay, so the first entry does not have a rows entry, and it's the filter function. It's 8 bits. And pixels ... fill is 2 depth per pixel multiplied by 2 pixels, right? So 2 depths per pixel times 2 pixels, and then we're gonna add 4 useless bits equals 8 bits. The next entry is rows 0, filter function 0. It has what appears to be a binary string, 3 zeros, a 1, and then 4 zeros. No, yes, 4 zeros, and that is 16. And we can make a quick check here. So this is 1, this is 2, 4, 8, and 16. So yes, that is 16 in binary. The last record, rows, is 1, so this is 0 indexed. The filter function is 0, and then we have another binary string, which is 176 in decimal, and we can also do a check there, so we can go 1, 2, 4, 8, and we have 16 and 32. 16 plus 32 plus 128. So 128 plus 16 plus 32 must be 176. We can do a really quick check here since 128 plus, I say 32 plus 64? Must be wrong there. Let's look at that again. So 1, 2, 4, 8, 16, 32, and 128. And that is 176. All right, so yes, so that checks out. Let's keep going. Filter functions. The filter functions are applied to the pixel data before compression to make the compression more efficient. In filter method 0, there are 5 filter functions. And so this is a diagram of pixels, and we are trying to calculate pixel x based on pixels C, B, D, and A. I don't think I've seen D actually used in a filter function, so it's mainly C, B, and A from what I understand, but let's look at the table. It maybe D is referenced within this table. So the filter function uses A, B, C to predict X. So yeah, it does not mention D, so I don't know why D is in the diagram, but whatever. So let's look at this. So we got type 0, none, original value. So no prediction at all, just take the literal value. 1 is sub, so byte A to the left. So sub is actually the direction. So the direction relative to X is a sub, so we're going to take A, and that is sub. Okay, so when we look at 2, that's up, so that's a direction up, byte B above, and if we look at that, we can see byte B. 3 is average, so the mean of bytes A and B rounded down. That's important, right? Because all of the byte values have to be integer values. There's no floating point here. And then number 4 is payeth or paith. I don't know how to correctly pronounce it, but it was invented by a guy named Andrew Paith. I think it was Andrew M. Paith. I could be wrong there. And it is A, B, or C, whichever is closest to P equals A plus B minus C. Which is, as far as I'm concerned, that's kind of like a different kind of average function, right? Because if A, B, and C were all 50, there would be 50 plus 50 minus 50. So it's saying, you know, take whichever one is closest to this weird average function. That's the way I interpret what path means. The filter function 0 means the data is original value, so we can decode previous scanline bits to scanline pixel indices. Scanline pixel indices. Rows, pixel index, and then fill ... So for the first record, we have rows 0, pixel index 0, 0, pixel index 0, 1, and then fill ... all zeros. And then the next row we have 1, pixel index 1, 0, pixel index 1, 1, and then fill ... is all zeros again. I'm not sure exactly what that means. Let's just keep going. With previously decoded palette, 255, 0, 0, 255. The next chunk, 0, 255, 0, 255. The next triplet with alpha, 0, 0, 255, 255. And the final RGBA chunk is 255, 255, 255 with 127 alpha, so it's 50% transparent, you could say. Scanline pixels, rows / columns, 0, and 1. So I believe those are just indices. Yeah, that makes sense because our image is just 2 by 2 pixels. So that means that your indices, if you were to give indices to the rows and columns, like kind of like chart it out on like a multiplication table kind of thing, you'd only have values 0 and 1. So what we're looking at here is the literal pixels in the proper position, but as a table. So the pixel on the top left is this one, 255, 0, 0, 255. The top right, 0, 255, 0, 255. And the bottom left, 0, 0, 255, 255. And the bottom right, 255, 255, 255, and 127. So it is red, green, blue, and then this is a white with 50% opacity. Or actually, that's 50% alpha. My mistake. Okay, so let's go down to chunk and 6. The bytes indices 127 to 130 inclusive, which is 39, 168, 232, and 87, which is a CRC 32 checksum. Chunk begins 7, 131 to 134 inclusive, 135 to 138 inclusive. The first one is 0, and then it spells out I end in ASCII for those last 4 bytes. 0 byte, I end critical chunk. There may be a constraint that says the critical chunk should always have a length of 0, and that's why you're seeing those 4 zeros right here. I can't quite remember, but I have a foggy, vague suspicion that I read that somewhere. Chunk data 7, I end, no data, right? Because it just marks the end of the data, therefore there's no data associated with it. It's like a end of line character, like a \end, like a carriage return. Okay, so chunk and 7, we have bytes 139 to 142 with the values 174, 66, 96, and 130 in decimal, and when we cram those all together to create an integer of 32 bits, we get a CRC 32 checksum. So the output image data is image data image data equals open curly brace width :2 comma height :2 comma data colon. We're going to open up our array literal, and we're going to pack 255, 0, 0, 255. So this would be our first pixel. Then we're going to pack in 0, 255, 0, 255. So that's our green. And then this is our blue. And, ooh, I may have... I did that wrong, so, okay, hold on. So, okay, yep, so this is red. Okay, that's our green. Okay, that's our blue. Okay, and this is our white that has 50% opacity. Okay, so conclusion. We have successfully decoded the PNG image from raw binary data to image data, but we have ignored a lot of side logic and details. Some are listed below. Bullet point, IDAT chunk can be split into multiple chunks, so when we should wait till we meet IN chunk before we decode the IDAT chunk. Okay, so that's going over how I said you need to concatenate all of those IDAT chunks before you decompress. You don't decompress the IDATs separately and then concatenate. You concatenate all of the compressed data together first, and then you decompress it all in one go. That's very important. Otherwise, I don't know, bad undefined stuff would happen, or I guess maybe defined bad stuff would happen. I don't know, but it definitely wouldn't work for you. There are 4 kinds of critical chunks and 14 kinds of ancillary chunks. See summary of standard chunks in PNG specification. Interlaced PNG are encoded in a way that gives the users feel the image is loaded faster, but gives the larger IDAT chunks. Okay, so they're talking about how, you know, interlacing kind of gives you a fuzzy preview of the image because it gives you, instead of loading all of the pixels in a sequential order, it kind of loads them in a way where you get a more physically distributed payload of pixels first. God, I am not explaining that well. There's other places that explain interlacing better than I am doing right now, so let's just keep it going. You can get the source code on GitHub, and then we got some references, the source code, the PNG specification, JavaScript PNG. I don't know what those kanji are, and even if I did, I wouldn't be able to correctly pronounce it and concatenate them together. Okay, and then no comments. Okay.